Welcome to the Hartman Polaritonic Matter Framework, or HPMF, a groundbreaking theoretical architecture that reimagines the very nature of matter using the dynamics of polaritons. Authored by James Hartman in 2026, this framework unifies light and matter at a fundamental level, enabling the engineering of new materials with properties never before possible. Imagine materials that can switch between solid and liquid states, or even resist gravity itself, all by manipulating light-derived quasiparticles. In this video, we'll journey through the core concepts, symbols, and mechanisms that define HPMF, setting the stage for a new era in material science and advanced engineering. At the heart of HPMF is the vision to engineer matter from the ground up, using the hybridization of light and matter. This approach leads to the creation of light-derived quasiparticles, liquid-like condensates, and even shock-induced solidification. The framework also introduces tunable, inertia, and gravity-resistant materials, opening the door to futuristic applications like lenticular craft hulls that can switch between different physical regimes. By controlling polariton dynamics, HPMF offers a unified path to programmable, adaptive, and resilient materials. To navigate the complexity of HPMF, a master symbol table organizes the key variables and parameters. These include the multi-flavor Polariton Spinor field psi, its components psi-j, effective masses mj asterisk, nonlinear interaction coefficients gjk, and coherent coupling terms jjk. The table also covers condensate properties like polariton density N, effective pressure Pn, and sound speed.cs. For structural order, symbols like phi, u, phi, and lambda describe the material's internal configuration and its coupling to light. Polariton parameters, such as effective mass density ρ and polariton momentum density ppol, round out the system, ensuring a comprehensive language for describing polaritonic matter. The foundation of HPMF lies in the hybridization of light and matter, where photons and excitons merge to form polaritons. This hybridization enables the engineering of dispersion relations, allowing for the freezing and liquefying of light itself. By carefully designing the microcavity environment, researchers can control the energy landscape, leading to the emergence of new phases of matter that blend optical and material properties. This chapter sets the stage for understanding how light can be manipulated to create entirely new forms of matter. Dispersion engineering is a core technique within HPMF, enabling precise control over how light and matter interact. By shaping the dispersion relations, scientists can tailor the behavior of polaritons, influencing their speed, mass, and interactions. This control is essential for creating liquid-like condensates and for inducing phase transitions between different states of matter. Dispersion engineering thus acts as the bridge between theoretical constructs and practical material innovations. One of the most revolutionary aspects of HPMF is the ability to freeze or liquefy light. Through polariton condensation, light can be made to behave like a fluid, forming a liquid-like condensate. Under certain conditions, shock-induced processes can solidify this condensate, creating a new class of materials with unique optical and mechanical properties. This dynamic control over the phase of light opens up possibilities for ultrafast switching and programmable matter. HPMF introduces the concept of multi-flavor polaritonic fields, where different flavors or types of polaritons coexist and interact. Each flavor is described by its own component psi-j, with unique effective mass and interaction coefficients. The Spinor-Pitaevskii equation, GPE, governs their dynamics, allowing for complex phase engineering and the creation of interaction manifolds. This multi-flavor approach enables the design of materials with tunable properties and adaptive responses to external stimuli. The Spinor-Pitaevskii equation, GPE, is central to modeling multi-flavor polaritonic fields. It describes the time evolution of each polariton component, accounting for kinetic energy, nonlinear interactions, and external pumping. The equation's structure allows for the emergence of rich dynamical behaviors, including shockwaves and condensate formation. By solving the GPE, researchers can predict how polariton fields evolve and interact, laying the groundwork for advanced material engineering. Phase engineering in multi-flavor polaritonic systems allows for the creation of materials with tailored optical and mechanical properties. By adjusting the relative phases and amplitudes of different polariton flavors, it's possible to design interaction manifolds that support exotic states of matter. This capability is crucial for programmable matter and for achieving precise control over phase transitions, such as those involved in shockwave-induced solidification. The mechanics of liquid-like condensates are governed by equations of state that relate polariton density, pressure, and chemical potential. Non-linear wave dynamics, including shock formation, play a central role in determining how these condensates behave under different conditions. Understanding these mechanics is key to harnessing the full potential of polaritonic matter, from ultrafast switching to robust structural transformations. The equation of state for a liquid-like condensate links the polariton density to effective pressure and chemical potential. This relationship determines how the condensate responds to external perturbations, such as injected pulses or structural deformations. By tuning the equation of state, researchers can design materials with specific mechanical and optical responses, paving the way for programmable matter. Shock formation occurs when nonlinear interactions in the Polariton field lead to abrupt changes in density and phase. By injecting a localized pulse, a dispersive shock wave can be generated, propagating through the condensate and triggering structural responses. The length, scale, and amplitude of the shock are determined by the effective mass, interaction coefficients, and the strength of the injected pulse. This process is central to the mechanism of shock wave to solid nucleation. The shock wave to solid nucleation mechanism is a Hartman original, providing a pathway for ultrafast solidification of polaritonic matter. When a shock wave propagates through the condensate, it can trigger a phase transition in the structural field, leading to the nucleation of a solid phase. This process is governed by a coupled Lagrangian that links fast polariton dynamics with slower structural deformations, enabling precise control over the formation and growth of solid regions. The coupled Lagrangian formalism integrates the dynamics of polariton fields and structural order parameters. Fast polariton dynamics are described by the first terms, while slow structural deformations are captured by the remaining terms. The coupling term $lambda psi2 phi dollar ensures that changes in polariton density directly influence the structural field, enabling rapid phase transitions and solidification events. Shock waves in polariton condensates are generated by injecting localized pulses, described mathematically by a delta function in time and a Gaussian in space. The resulting nonlinear dynamics produce a dispersive shock wave, with its length, scale, and amplitude determined by the effective mass, interaction coefficients, and pulse strength. These shock waves are the driving force behind rapid phase transitions in the structural field. The structural field responds to polariton shock waves through its own equation of motion, which includes inertia, stiffness, and a multi-well potential representing different solid phases. The coupling to polariton density ensures that when the shock wave is strong enough, it can push the structural field over a potential barrier, initiating a phase transition. Each well in the potential corresponds to a distinct solid phase, allowing for programmable material properties. A phase transition is triggered when the polariton density exceeds a critical threshold, overcoming the energy barrier between two solid phases. This nucleation condition is given by $lambda psi 2 is greater than delta U alpha beta dollar, where delta U alpha beta dollar is the difference in potential energy between the two phases. The critical polariton density $n crit sets the minimum requirement for solidification to occur. The nucleation radius determines the size of the initial solid region formed during a phase transition. It is found by balancing the structural stiffness against the polariton pressure, leading to the relation $R nuc sim k phi gn $2. This radius sets the scale for the growth of the new phase and is a key parameter in designing materials with controlled microstructures. Once nucleation has occurred, the solid region grows according to the equation $-cracked A dt equals 2 rho phi lambda n delta U alpha beta dollar. Growth accelerates with increasing polariton density, allowing for ultrafast solidification. This dynamic process enables the creation of flash-made polaritonic solids, with applications in rapid manufacturing and adaptive materials. To anchor the theoretical framework, HPMF provides example parameter sets for polariton and structural fields. These include effective mass, interaction strength, density, stiffness, inertia, and coupling constants. While not experimental values, these parameters define the design space for engineering polaritonic materials and guide the selection of materials and device architectures. Using the baseline parameters, HPMF predicts critical polariton densities, nucleation, radii, and growth rates for solidification. For example, a critical density of $10 for μm, negative $2, nucleation radius of $0.3 μm, and growth rate of $0.1 μm PS dollar are achievable. These results demonstrate the potential for ultrafast, programmable material transformations using polariton dynamics. HPMF enables the creation of programmable matter by leveraging multi-well structural potentials and phase-selective writing. By controlling the binding topology and phase transitions at the atomic scale, materials can be customized for specific functions. This capability is foundational for next-generation devices, adaptive systems, and intelligent materials that respond dynamically to their environment. Multi-well potentials in the structural field allow for the coexistence of multiple solid phases within a single material. By selectively writing or erasing phases, materials can be reconfigured on demand. This approach provides unprecedented flexibility in material design, enabling the creation of complex, hierarchical structures with tailored properties. Phase-selective writing enables the targeted creation or erasure of specific solid phases within a material. By controlling the local polariton density and structural field, regions of the material can be programmed with desired properties. This technique is essential for building reconfigurable devices and adaptive systems that can change function on the fly. Binding topology control refers to the ability to manipulate the arrangement and connectivity of atoms or molecules within a material. By leveraging polariton dynamics and structural field engineering, HPMF allows for the design of materials with custom binding topologies, leading to novel mechanical, optical, and electronic properties. One of the most futuristic aspects of HPMF is the engineering of gravity-resistant materials. By shaping the inertial tensor and redistributing stress energy, materials can be made to resist gravitational forces. Dynamic stiffness control further enhances this capability, enabling the creation of structures that maintain their shape and function under extreme conditions. Inertial tensor shaping allows for the directional control of a material's response to forces, including gravity. By engineering the distribution of mass and stiffness at the microscopic level, materials can be designed to exhibit anisotropic inertia, making them resistant to deformation or collapse under load. Stress energy redistribution involves the dynamic allocation of internal forces within a material to counteract external stresses, such as gravity. By modulating the polariton field and structural parameters, materials can adapt their internal structure in real time, maintaining stability and function even in challenging environments. Dynamic stiffness control enables materials to adjust their rigidity in response to changing conditions. By tuning the structural field and polariton interactions, materials can become softer or stiffer as needed, providing resilience against mechanical shocks and environmental fluctuations. HPMF extends its reach to the design of advanced craft hulls, particularly lenticular structures that can switch between quasiparticle and particle regimes. These hulls embed polariton channels, enabling propulsion and adaptive responses to external forces. The architecture is optimized for both strength and flexibility, leveraging the unique properties of polaritonic matter. Quasiparticle-particle switching allows craft hulls to transition between different physical regimes, optimizing performance for various operational scenarios. By controlling the dominance parameter, $chi$, the hull can switch from a quasiparticle-dominated state, ideal for energy absorption, to a particle-dominated state, optimized for structural integrity. Hull-embedded polariton channels provide pathways for controlled energy and momentum flow within the craft structure. These channels enable advanced propulsion methods and adaptive responses to external forces, making the craft highly maneuverable and resilient. Propulsion in lenticular craft hulls is achieved by exploiting anisotropic Polariton momentum. By directing Polariton flows along specific channels, the craft can generate thrust and maneuver with high precision. This method leverages the unique properties of polaritonic matter, offering new possibilities for advanced transportation technology. The appendices of HPMF provide comprehensive symbol tables, parameter sets, and scaling laws. These resources ensure that researchers and engineers can accurately interpret and apply the framework to a wide range of materials and devices. The symbol tables cover all key variables, from Polariton fields to structural parameters and hull properties. Parameter sets define the operational ranges for polariton and structural fields, guiding the selection of materials and device architectures. Scaling laws provide the mathematical relationships needed to translate theoretical predictions into practical designs, ensuring that HPMF can be applied across different length and timescales. The visual language of HPMF is anchored by ultra-realistic cinematic diagrams that depict lenticular chamber geometries, photon-exciton coupling zones, frozen light basins, and multi-flavor polariton channels. These visuals not only clarify complex concepts, but also inspire new directions in material science and engineering. The Chapter 1 poster, rendered in ultra-realistic style, visually anchors the Hartman Polaritonic Matter Framework. It features a lenticular microcavity, frozen light basin, liquid light condensate, and spectral polariton channels, all integrated with engraved authorship. This image sets the tone for the entire visual dossier, combining scientific rigor with artistic clarity. The Hartman Polaritonic Matter Framework was conceived by James Hartman on the 14th of January 2026 in Gary, Indiana. This origin story underscores the innovative spirit and forward-thinking vision that drive the framework, positioning it as a cornerstone for future advances in material science and engineering. Looking ahead, HPMF opens up a vast landscape of possibilities for programmable matter, gravity-resistant materials, and advanced craft architectures. Ongoing research will expand the framework, refine parameter sets, and develop new applications, ensuring that HPMF remains at the forefront of scientific and technological innovation. In summary, the Hartman Polaritonic Matter Framework provides a unified, versatile platform for engineering new forms of matter. By harnessing the interplay between light and structural fields, HPMF enables rapid phase transitions, programmable properties, and adaptive responses. Its comprehensive symbol tables, parameter sets, and visual language make it accessible to researchers and engineers alike. The impact of HPMF extends across multiple domains, from material science and photonics to aerospace and adaptive systems. Its principles enable the creation of materials with unprecedented properties, supporting the development of next-generation devices, vehicles, and infrastructure. As research progresses, the framework's influence will only grow, shaping the future of technology. The Hartman Dossier is designed to be an evolving resource, with each chapter building on the last. As new discoveries are made and new diagrams rendered, the framework will continue to expand, offering deeper insights and more powerful tools for material engineering. Stay tuned for further chapters and visualizations. We invite you to explore the Hartman Polaritonic Matter Framework in depth, whether you are a researcher, engineer, or enthusiast. The concepts and tools presented here offer a gateway to the future of material science. Dive into the chapters, study the diagrams, and imagine the possibilities that lie ahead. Thank you for joining us on this journey through the Hartman Polaritonic Matter Framework. As we move forward, new chapters and diagrams will continue to illuminate the path toward programmable, adaptive, and resilient materials. The future of matter is bright, powered by the fusion of light and structure. Stay curious and stay inspired.